working, is it? Okay, fine.
This is only for web telecast.
Got it. Okay, fine. I'll do that in just 1 second.
Doesn't cover most of these because he's.
मैम telecast भी ये भी चल जाना मतलब यदि आवाज़ बाहर नहीं होनी तो telecast हो जाएगा पीछे इत्थों तो दूसरी आवाज़ तो चल ही रही है फिर वो तारां वगैरह बहुत छोटियां ना छोटियां क्रॉस में एडजस्टमेंट करनी
coordination of numbers and things along those lines. And then we moved on to talk in quite a lot more detail about the applications of organometallic ligands in lanthanide chemistry. For two reasons. One, because it's interesting and it's important, but also because it's a very large part of the work that my group does in Manchester. So we'll be building this up as a theme as we go along. That, I guess, got us roughly up to about this point yesterday. So in today's lecture, what we're going to do is take some of the main principles from lanthanide chemistry and look at the electronic structure in a bit more detail with a view to looking at magnetic properties. And I think it is true to say that the lanthanides do have a number of fairly unique, distinct properties. But to try and put them into some sort of familiar context, what I will do is start by talking about transition metals, which I guess you already know about from previous lecture courses. So that, if you like, is the plan for today. We will start with that topic and then we'll move on to look at eventually item number 4 on the agenda. So item number 4 on the agenda, as I would have explained to you already, is a workshop or a problem sheet, which I have right here, okay? So I will distribute these sheets to you after the lunch break, and depending on how we're doing for timing, okay, the idea is that during that session in this room you will work on that problem sheet and I will circulate amongst you, answer any questions that you might have, but the idea is for you to test your knowledge as we go along rather than just for you to listen to me for the whole week, which I guess is a little bit boring, okay? So at some point today, probably after lunch, okay, you guys will be doing a little bit of work yourselves. And the idea is that when the course is finished, you can hand the work in and the work can be graded, and eventually I'll provide you with an answer sheet so that you can work out where you've gone wrong or where you've gone right with these questions. Some of the questions are very easy and some of them are a little bit more taxing, but the idea is it's important for you to be testing that as you go along. Okay, so that's the plan for today. What I would like to do as well here is just focus on item number 10 on the agenda. Okay, so I guess most of you will recall what the plan for that one is, okay? Some students will be selected to give presentations, so standing here, for 1 minute each on a particular element. Okay? I have already selected those 15 people, and if you've been selected, you should have received an email from me this morning. Okay. So what I will do is give people a chance to check their emails, and I'll ask the question again, because if some of those people are not here, clearly I need to pick some other people. Okay, so if it's possible for you to check your emails during the course of today, that would be very helpful. The presentations themselves, the plan is for them to happen at some point on Thursday afternoon. Okay, so all you need to do for that is prepare 2 slides, okay, involving PowerPoint, send them to me. I will transfer them all to my laptop, and in principle things will work very smoothly. Okay, so please check your emails today to find out if you are one of the 15 lucky winners in this process. Okay, thank you. Right, that is the plan. Here is the start of today's lecture. Okay. So the plan in the build-up to the lunch break today is to talk in quite a bit more detail now, particularly about the magnetic properties of 4F ions, and where relevant I will talk about some of their spectroscopic properties as well. So the aim here then, as I mentioned, is to put things into a more familiar context based on transition metals. So my feeling is, given where you are with your studies at the moment, that everything on this slide will be familiar to you already. Okay, but I'll just emphasize a few key principles. So, what do we know about transition metals? Well, because we're talking about lanthanides, and we know that the common oxidation state is +3, okay, we'll start with a direct comparison of the transition metal ion in the +3 oxidation state, titanium 3+. Simple case, because titanium 3+, as you are well aware, is a D1 species. Okay, so that's as simple as it can be. If we take titanium 3+ as an ion in the gas phase, no ligands involved whatsoever, we have a free ion situation in which our 5d orbitals are completely ejected. Okay, and that is the case because we have no ligands, therefore there's no directional preference for energy. Then what we do is take our gas phase ion and surround it with a group of ligands in a common environment, which of course for titanium 3+ is octahedral. So you already know then that when you place a transition metal ion in an octahedral environment, 3 of the d orbitals are stabilized relative to the free ion situation, and 2 of those d orbitals are destabilized relative. So, what we have then, in our ground state electronic configuration, is an electron in one d orbital. There's no reason why it should prefer one of those 3 d orbitals over the other 2. So it is possible then for the electron to be in this one, and this one. The impact of that is that angular momentum that arises from the individual electron also experiences an orbital contribution. So the migration of the electron across a manifold of degenerate d orbitals. So we have a spin contribution to the total angular momentum and an orbital contribution, and these 2 species can couple together to generate an overall output. So the extent to which spin-orbit coupling occurs can be quantified by means of the so-called spin-orbit coupling constant. Okay, the spin-orbit coupling constant is given this symbol here, the Greek letter zeta. And for a free ion species, so in this environment over here, for the +3 transition metal ions, clearly copper is not a +3 ion in a stable context, but it can be calculated. Typically speaking, the numbers are in the region of 154 to about 900 waves. What does that actually mean in terms of what we're looking at here? Well, if you compare a typical spin-orbit coupling constant to a typical crystal field splitting, quite obviously, this is very small compared to this. So what we can say is that the spin-orbit coupling is a secondary minor perturbation on the overall energy spectrum, such that the crystal field or the ligand field, depending on what terminology you want to use, dominates the spin orbit coupling. I should mention as well, for those of you writing things down, you will be provided with these lecture notes at some point quite soon. Okay, that's no problem. Okay, so that was the situation with the transition metal. That actually turn out to occur in reality as well. So here's a lanthanide 3+ ion in the gas phase, no ligands whatsoever. By definition, the 7 f orbitals are degenerate. If we take lanthanide 3+, and thousands in some cases. So what we're seeing here, in terms of crystal field splitting, is a difference of orders of magnitude. So a very, very different picture. So a crystal field splitting, a few hundred wave numbers is completely typical for lanthanide, with very little variation across the lanthanide series, actually. If we now look at the spin-orbit coupling constant, exactly the same, for 3+ lanthanide ions in the gas phase, if you compare it to what it was with transition metals, clearly now it's much bigger. Several hundred wave numbers for the earlier lanthanides, about 1,000 for the lanthanides in the middle, and then by the time we get to the right-hand side where the heavy ones are, it's of the order of a few thousand wave numbers, so really quite different. So if you compare that to the thermal energy at room temperature, which is about 206 wave numbers, it's clear that the crystal field splitting is actually insignificant, really very small indeed. In contrast to that, the spin-orbit coupling is large compared to the thermal energy that's available at room temperature. The ligand field splitting in a lanthanide complex at room temperature is insignificant, and yet actually also turns out to be independent of the ligand. Key point here is it's an approximation, and I'm talking about room temperature. What does that mean? Well, when it comes to interpreting in a theoretical sense the properties of a lanthanide cation in a real complex that you can synthesize in the laboratory, you can do so in terms of this picture over here, the free ion. Okay, because it's very similar to the real picture over here, and therefore less complicated. So the way in which we start to interpret the properties of lanthanide complexes is according to something referred to as the free ion approximation. Okay, the free ion approximation, which means the properties of lanthanide 3+ in a real complex can be approximated to those of a lanthanide ion in the gas phase. So we'll talk about that in a little bit more detail now. So we'll be talking quite a bit about spin-orbit coupling at this stage, and I'm going to pick one example just to highlight a few general principles. Those of you who know about single molecule magnets, okay, will already be aware that dysprosium accounts for about probably 95% of all known examples. Okay? Making a single molecule magnet is easy. Okay, just add dysprosium and you probably will get a result. Okay? So I will talk about that. Now, based on what I've already told you about electronic configurations, it should be relatively straightforward for you to work out that dysprosium 3+ has a configuration of F9 in the count state. If you want a quick way of working that out, just by scanning the periodic table, gadolinium 3+ is right in the center of the F block. Okay, so that's an F7 species, completely isotropic, and dysprosium is 2 elements to the right. So gadolinium F7, dysprosium F9. In terms of our approximation, okay, just going back one slide, this situation here, and here actually, we can represent like this in a bit more detail. So these are the 9 F electrons, 7 pointing up, 2 pointing down. Each individual F orbital, okay, has a well-defined value of the magnetic quantum number, which I'm assuming that you know about. Okay, so for an F orbital, L equals 3, which means that the allowed values of ML are ±3, ±2, ±1, and 0. Okay, you'll be tested on that in these question sheets later on today. So, what we need to do to represent spin-orbit coupling in a convenient way is develop some shorthand notation that allows us to develop something called a term symbol, okay, which for lanthanides is a very important thing to be able to do. So what we need to do then to generate a picture of the spin-orbit coupling is first of all consider the total spin, then consider the total orbital contribution, and then see how the spin-orbit coupling combines those in a useful manner. So, the first part, I would hope, is something that you already know about. Okay, so the total spin in your system is the sum of the individual spins on each electron. So, in my version of this presentation here, the electrons pointing up are in red, okay, not in black, and the ones pointing down are actually in black, okay. And these numbers here are also in red, as are these. So when you get this version of the PowerPoint slide, it will be much clearer. So what we need to do then, to work out the total spin, again, this is relatively simple, I think. 7 electrons with a spin pointing up, which we'll say is plus a half, minus 2 electrons pointing down, gives an overall spin of 5 over 2. Fairly simple from that point. For the total orbital contribution, okay, first of all we need a positive number here, so we take the modulus. This is the sum of the value of the individual ML quantum numbers. Okay, so if we take the 7 pointing up, quite obviously we have 1 in each, okay, so it's 3 plus 2 plus 1 plus 0, minus 1 minus 2, minus 3, okay, that takes care of all 7 electrons pointing up. Then we have 1 pointing down, minus 3, 1 pointing down, minus 2, okay, that actually gives a value of minus 5, okay, we can't have a negative number because the sums don't work if we do that. So the total orbital angular momentum is 5, okay. So, because we now have 5 allowed value, okay, the maximum value is L plus S, the minimum value is L minus S, and the allowed values in between proceed in integer steps. Okay, so for dysprosium then, we have 5 plus 2.5, which is 7.5, and this is conventionally represented as 15 over 2. L minus S is 5 over 2, and if we take integer steps, it's 13, 11, 9, 7, and 5. So these are the allowed values of the spin-orbit coupling for a dysprosium cation. Okay, so what's expected of you then, in terms of looking at different lanthanides, is to calculate similar schemes based on what I've shown you here. Once you've learned the method, the application to other systems actually, I think, is relatively simple. Okay, so we can use this information now to generate terms of L. Okay, the convention says that each value of L corresponds to a letter. And what you will find with lanthanides is, when we're talking about ground state certainly, the maximum value of L that you will encounter is 6. So that's more than you get with the transition method, okay, with the maximum value of 6. Each number corresponds to a letter, and it is a letter that we use in our term symbol. The key point here is, when we're determining which letter to use in the term symbol, you have to start counting from 0, okay, not from 1. Based on my experience of teaching this work in Manchester, if somebody makes a mistake, only one of these for dysprosium represents the true ground state. The convention is, when you have a configuration that is less than half filled, okay, when you have a configuration that is less than half filled, the smallest value of J defines your ground state. Here as well, because we have more than 7 F electrons, the maximum value of J defines our ground state. Okay, so for dysprosium, the ground state term symbol comes out as being this. Okay, so it's this kind of thing that you are expected to know about, because this is extremely useful as a starting point for interpreting magnetic properties. Okay, so that's the ground state. In terms of the ground state relative to the other states, of which there are quite a few here as well, we can define an energy. Okay, what I'm not doing is work through the derivation of this because it's long and frankly not very exciting. Okay, but what we can do is express the energy of an individual J term in terms of the spin-orbit coupled quantum number, the orbital contribution and the spin contribution in terms of parameter lambda, okay, which I'll come back to in just a second. The difference in energy between two J states, okay, is delta E in terms of J and J plus 1, where lambda appears again, and the J for the lowest term is specified here as well. Lambda is one of these constants that emerges from a detailed theoretical treatment. Lambda LS is a constant which can be defined in terms of the one electron spin orbit coupling constant, okay, which I've already told you about. So now we're coming back to this term zeta, okay, in which your lambda term is determined as two possible values relative to the spin. Okay? Because of time constraints, there really isn't enough time available to go into the detailed derivation of things. Safe to say, some of the more established magnetochemistry textbooks actually talk about this in quite a lot of detail. Okay? I'm fighting against the birds out here in terms of quality. We need cats. Okay. So, electron spin orbit coupling constant. This is a situation in which we have a shell that's less than half filled. When we have a shell that's more than half filled, the negative version of the one electron SOC defines your ground term. What you're doing here in this formalism is effectively taking the value of J that has the largest negative magnitude, or conversely, the smallest positive magnitude, okay, which means lower in energy. The largest negative magnitude, or the smallest positive magnitude, which means lowest in energy relative to the others. Okay, so we can see then, if we look at dysprosium here, if we have minus 15 over 2, okay, as our ground state, then the negative value is very low indeed. If we had 5 over 2, then it's not quite as low. For samarium, it would be the other way around. Okay, so this is the origin of that particular effect. So, there is a change in sign of lambda depending in which half of the F block you actually observe, which half of the 4F series. So an anti-parallel arrangement of L and S occurs when n equals 7, and this refers to this part over here where zeta takes the negative sign. A parallel arrangement occurs when you have more of these things. So what this is effectively saying is the orbital and spin contributions oppose each other, which in a very, very arm-wavy sense means doing this, okay? Whereas when you're beyond halfway, they tend to stabilize each other when they're both oriented in the same direction. Okay? The spin and orbital contributions can augment or oppose each other, and where they do that depends on where you're at in F block. Okay, if that's the good news is that when we're talking about magnetic properties of lanthanoid ions, usually you only need to think about the ground state. Okay? Two exceptions to that, which I will mention in just a second. But if you're talking about single molecule magnets, the chances are you're in the ground state and that's where you can stay. Okay. So, here are the results in the context of term symbols for all of the lanthanides. Okay. All this information is extracted from textbooks. Okay, it is widely available. So here we have the lanthanides, their F electron configurations, and the various term symbols. And what you can see, I think, when you look at these, is that certain terms are symmetry related. So if you know the result for one lanthanide, you can work it out for the others. So I've just told you about dysprosium, sextet H 15 over 2. The symmetry related species is here, sextet H 5 over 2. You can see the difference actually lies in the J values. So samarium is related to dysprosium. Okay, why is that, you may wonder? Samarium is an F5 species, so there are two empty F orbitals. Okay, dysprosium is an F9 species, so there are two electrons pointing down to generate the anisotropy. So the two vacancies in samarium are symmetry related to the two electrons pointing down for dysprosium. So these symmetry relations are actually very important. And actually, the point of symmetry in the F block comes with gadolinium. Okay, so if you notice here, gadolinium in the center, there is no symmetry-related species really for this one. But look at europium, related to terbium, both F terms with a 7. Samarium, dysprosium I just mentioned. Promethium, 5I. Holmium, 5I. They only differ in terms of their J value. So these symmetry relations spread out from the center. So if you can work it out for one, you can work it out for the other. That's useful. Now we come back to zeta, this spin-orbit coupling constant. I told you that it varies across the series. You can see as the atomic number of the element increases, there's a fairly substantial increase in the value of zeta. So you start with cerium, where it's a few hundred wave numbers, gadolinium in the middle, about 1500, and then quite large with ytterbium at the end. Couldn't find a value for lutetium, so if anybody finds that, please tell me, because I quite like to. Okay, now we look at the magnetism in slightly more detail, okay? I have told you that for lanthanides, we can interpret the properties of their complexes in terms of a free ion approximation. Okay? So does that actually work out in reality? Actually, yes, it does, and surprisingly well. So this is a calculated effective magnetic moment based on 7 degenerate f orbitals, in this instance with cerium with 1 f electron. You can calculate mu f, mu effective, in units of Bohr magnetons, according to this equation down here. So G is a constant defined by numbers that you can calculate pretty easily. Okay, just simple arithmetic here. And the value of J in the ground state, you can calculate that pretty simply. This is the calculated value. The observed values match up very well for this element, as they do for this one and for this one. Promethium, certainly you can calculate an effective magnetic moment, but nobody's had the courage to measure it because promethium is intensely radioactive. Okay, so probably it would be correct. The only two differences are here, samarium and europium. They're quite unusual. So calculated value 0.85, measured value usually quite a lot higher. Okay, sometimes double. Does anybody know why that is? Samarium is relatively unusual in that the ground term is reasonably close in energy to at least one excited state. Okay, so you can have second order effects, low-lying excited states. The same applies to europium as well, which in principle should be diamagnetic. Again, it has J equals 0 in the ground state, but actually the measured moments are significant, account for the vast majority of lanthanide single molecule magnets. That turns out to be important, and is certainly something that we will come back to. Okay. Happy so far? Nobody's walked out? Okay. Right, we're in for time. This expands on things in a little bit more detail, so we can look at the energy spectrum in a slightly more sort of holistic context. So we have implemented something called dynables. Okay, clearly that turns out to be nonsense, because covalent factors are very important, and you can't explain the properties of transition metal complexes unless you involve covalent character. So what we'll do with lanthanides is question the same assumption. What we're saying is ligand field effects don't matter for lanthanides. Free ion in the gas phase with no ligands is the same as a complex in a real situation. So we'll start to question. Is the ligand field splitting really insignificant? So again, looking at dysprosium, we've talked about this previously. Okay, you can now derive this term based on what I've told you. The sextet H term is shown here. Okay, this, if you like, is the term involving only inter-electron repulsion. So we have not yet applied the spin-orbit coupling to this term. If we apply the spin-orbit coupling, we've said in our ground term, 15/2 is defined. Okay, so that is the ground term. Here is an excited term, and you can see the H terms start to build up. You also have terms arising from different configurations of the spin. Okay, but you can see in terms of energy differences, they're quite significant and unlikely to matter at room temperature. In room temperature, the energy is about 200 wave numbers. Here, the difference is a few thousand. So we're only concerned with this term, and we're only concerned with this spin-orbit coupled term here, because the energy gap is again a few thousand wave numbers. This picture is very similar to what you obtain for all of the lanthanides except samarium and europium. Sometimes the gaps are very large. If, for example, we consider gadolinium, the gap between the ground spin-orbit coupled term and the first excited term is about 30,000 wave numbers. It's enormous. It's never going to cause you any problems as a magnetochemist. Okay, So what about the crystal field splitting, which I have said is not significant? Well, there is a rule which, just like the spin multiplicity, the value of big S gives 2S plus 1 microstates, so too does a value of J give 2J plus 1 microstates. Okay? So the orbital degeneracy of our system here, 15/2, is actually 16. That means the spin-orbit coupling momentum can project itself in 16 different ways for a single ion species. Now there is a rule, the origins of which I have to confess to you I really don't understand, because it's quantum physics going back 60, 70 years. Okay, but what I do know is the result, okay, and I can explain to you why it's significant. Okay, so 2J plus 1 system, where J is 15/2, has a 16-fold degeneracy. This is the situation in a free ion. They are indeed degenerate because you have no reference frame, no ligands, no X, Y, Z, nothing like that. When you put this species in a regular complex, your 16 degenerate species become 8 pairs. Okay, so the allowed values, let's just say for the ground state, are plus 15/2 and minus 15/2. We'll come back to that in just a second. In a complex, they become a pair and they become degenerate. And these pairs are referred to as Kramer's doublets. Okay, Kramer's was I think he was Dutch. He was the physicist who worked out that these things should exist as pairs. Crucially, okay, a Kramer's doublet refers to a system that has an odd number of electrons, which for dysprosium actually is correct. This gives rise to something called Kramer's Theorem, okay, and this is a quotation taken from the original paper, which says that the energy levels of a system that contain an odd number of spin half particles, okay, so an odd number of F electrons in our context, are at least doubly degenerate in the absence of an external magnetic field. Okay, so what that means then, you have 16 degenerate levels in the free ion, split into 8 pairs, and the 8 pairs are known as Kramer's doublets. For a system that has an odd number of electrons, okay, that will always be the case. Even numbered systems turn out to be standard. Really, the true origins of this consider things like time reversal symmetry, which is really well beyond the scope of what anything that a chemist will want to look at, so we're not going to talk about that. So this is Kramer's theorem. What does that mean for dysprosium? So the first 2 bullet points here summarise the picture on the previous slide. Okay, so the crystal field is subordinate to the spin-orbit coupling interaction. Okay, what that means, if I go here, spin-orbit coupling is very big, a few thousand wave numbers. Crystal field is very small. Okay, this is just illustrating something we've already talked about. Okay, so 16-fold degenerate splits into 8 pairs. It may not be visible with the resolution here, okay, but here are 8 energy levels, each of which consists of 2 different orientations of the same number, 15/2. Okay. So, if we're talking about crystal field splitting of a few hundred wave numbers, at room temperature it's not significant, at low temperatures it is significant. Okay? You're only talking there about a few wave numbers worth of thermal energy. Temperatures, where we do a lot of magnetochemistry, it is actually quite important. So it is the interaction then with the crystal field, so the ligand environment, with the ground J term, the free ion, okay, that is responsible for the observation of single molecule magnet properties or not, okay, because you don't always get them. And usually when you don't get them, you can interpret in terms of this. So coming back to our example, which is dysprosium, with the ground term here of sextet H 15/2. Our value of J, 15/2, gives rise to a series of MJ values, and I've told you that there should be 16. Okay, 2, 4, 6, 8, 10, 12, 14, 16. Okay, those are the values of MJ for your ion in a crystal field. Okay, so the MJ projections are degenerate in a free ion, but in a real complex, the degeneracy of these systems is lifted. Each of these has a different magnitude and direction, therefore they interact with their environment in a different manner, therefore they have a different energy. Okay? Therefore, you have a crystal field split manifold. And for dysprosium, it comes out looking like this. Okay? So it looks a little bit like a crystal field splitting diagram. It's important to point out that these do not represent energies of F orbitals, okay? They represent energies of MJ states. Quite different. So each of these then exist as a pair, and they are degenerate, and these pairs are your Kramer's liquids. What I've done here is present the ideal situation for dysprosium. The reason it's ideal is because the largest value of MJ is at the bottom, the smallest value of MJ is at the top, and the other ones stack up in numerical order. Okay? The temptation is to assume that this is true in all complexes, and actually the answer is that it is not true. Okay? You have to determine that, which is actually most easily done by theoretical methods, but there are other methods available as well. So in terms of the splitting, clearly it depends very much on the ligands that you have, but if you get the coordination geometry right, you can stabilise the ground state relative to one or more of the excited states to a fairly significant extent, but it requires a bit of thought, and we will see some examples of that. But nonetheless, sample a magnetic moment, so the bigger the value of MJ, the bigger the magnetic moment. Under normal circumstances, they would have an equal population. Okay, therefore your sample has no net magnetisation because the two orientations are exactly opposite. In a single molecule magnet, however, only one of these two is populated, and therefore your material is magnetised, making it just like a regular ferromagnetic material. So what we're trying to do as coordination chemists is engineer things such that we can populate one of these and not the other, and have a very large gap between the higher lying states. That turns out to be extremely difficult. Okay, but nonetheless, my group and other groups have made some progress with that, and I'll tell you about some specific examples later. Before we dive into that, before we break for lunch, I guess actually, summarise a few key points here. Just jumping on there, I'll come back to that later. Okay, so in terms of the energy gaps here, okay, the magnitude of this crystal field splitting is determined by the ligands. That should be obvious to you, okay, but I think it's important to point that one out. Crystal field splittings for transition metals are also determined by the oxidation state, okay, which for lanthanides, because that doesn't change, that's not a consideration. The magnetic moment of your sample is determined by the population of these MJ levels, so you can get it to be in the region of 1,000 wave numbers, sometimes higher, okay, versus thermal energy at room temperature. So this means then at room temperature...
Very hard to say.
Do you mean lambda or zeta?
Lambda.
So these properties are dependent to some extent on the atomic number. I think it increases as z to the 4.
Yeah.
So the answer that I can give you is that it goes up with the atomic number. Beyond that, I'm afraid my... So it goes as z to the 4, which is a very strong dependency, actually.
Yeah, yeah. But that is what is written in the books most of the times. Dependent upon z effective. And every time my class looks at me, how come?
My temptation is to explain it in terms of relativistic effects, but I can't really go any further than that, I'm afraid.
And earlier when we teach them this Russell-Saunders coupling and JJ coupling, when we say that JJ coupling is more appropriate for heavier.
The ab initio calculations take a more accurate approach to it, which is why we use them so often.
Only in the actinides.
Well, for heavier lanthanides... Yeah, that's right. So